and thank you for coming to my talk. Thankfully, after lunch, when everybody's a little bit tired, we're going to have like a really light topic talking about binary exploitation. If you're going to fall asleep, like go to the back so I don't see you. No, just kidding. My talk, this is actually the first slide I made for my talk, living in the future. Because we like to think we are living in the future, like tech has come so far, we are, things are so different. And only yesterday I was talking to someone and they said, actually when you think about it, like the stuff that we have now is basically the stuff we had 20 years ago, it just works now. But this talk is a little bit about how this living in the future basically is sometimes just reliving the past. So I'm going to have this kind of split between systems programming, which is where I come from. I do C++ programming, sometimes do C programming, and binary exploitation, which has sort of been something I've been loving to play with for the past few years. And how these two disciplines have a very distinct culture and distinct communities that often don't overlap much, and therefore have their own lore and their own progression in what they learn and the tooling that they use over time. So I'm going to kind of envision that with these timelines. So I'm going to start at 2000. It was a randomly chosen number. I could have chosen something earlier. And we're going to bring it up until today. And I'm going to show, this is how I'm going to try to illustrate the distance in time. So for the boomers in the house, 2000, that was Y2K. For the zoomers in the house, Taylor Swift was 11 at that time, which is scary for all of us. Okay, so the talk is called Classic Vulnerabilities, and I should introduce myself. So my name is Patricia Aas. I'm a trainer and a consultant. I'm a C++ programmer. I've been specializing in application security, and then specifically in C++ application security over the past few years. I work for TurtleSec, and a bunch of TurtleSec people are here today, so this is really awesome. So this is a company that I helped, where I co-founded a few years ago, and before that I worked at, so my first real job after university was at Opera Software, working on the original Opera browser back in 2005. And then I was even a Java consultant for a couple of years, and then I worked at Cisco making telepresence systems there, and then I went back to making a browser. And as someone reminded me in the break, I was also making browsers while I was at Cisco, so. Yes, so I have a master's in computer science, and my pronouns are she, they. But what do I know about this topic? Like, why should I talk to you about it? And I guess it's because of this intersection of these two communities, and I'm kind of on the middle of that. So I teach some classes in C++, so I have this mod C++ fundamentals and intermediate, but I also have a totally different class that I teach, which is called Insecure C++. And in Insecure C++, I teach C++ programmers basics of exploitation, basically. And that's trying to bridge kind of those two communities. It's a really fun class to teach because I can get really advanced because these people already know C++, right? So there's so many things I don't have to cover, so I can actually cover a lot. So I've had a lot of fun with this. But let's go back in time. So back to 2000. So I'm sure everyone who was like sort of a semi-adult around 2000 knows sort of where they were, like New Year's Eve 2000. I was on a beach in Costa Rica at the time. But what I think of when I think more of this period of my life is that over here, that's when I finished my bachelor's degree. It will help if I show you the graph. It was there. That's when I finished my bachelor's degree. For people who don't like recognize this graph, I can help you. That was peak.com. That was when like if you knew one tag in HTML, you could get hired. It went literally downhill from there. And so when and that's unfortunately also when I started my bachelor's degree. So, so by the time I'd finished my bachelor's degree, it was absolutely impossible to get a job, and so I got a master's degree. But for the rest of you, you might remember it as, well, okay, I'm going to remind 2000 was 22 years ago. It's scary. But it was also the year that Say My Name by Destiny's Child was on the charts, and NSYNC had Bye Bye Bye. And for I guess we'll have to go for the millennials in the house. This was before Beyonce and Justin Timberlake did their solo careers. So, yeah. I was listening to the NSYNC thing yesterday and dancing in the office. Anyway, and I said that on YouTube now, so it's over. But in July of 2000, another thing happened, and that's sort of why I want to bring home how long time ago it was. So in July 2000, solar designer, also known as Alexander Pesliak, published what was named and has been referred to later also as the first generic heap exploitation technique. And so we're going to spend most of this presentation probably on you understanding this technique. So he was targeting malloc implementations, and in his description he was talking specifically about this Douglas implementation of malloc, but this went back to basically a good chunk of all of the malloc implementations had similar vulnerabilities. And the reason for that, and I've thought about that a lot because I teach this in my training, and I think the reason for that is that the problem of malloc is such a small problem, and the constraints are very well known that people end up having very similar implementations. So the idea that Solar Designer had was if we could make some kind of portable exploit, like if we were going against the allocator, the system allocator, then we could have some kind of exploit that would work against many different applications. And so the time and effort we have to put into it, we could amortize that over many different exploits. I mean, there's economics and everything, right? So we're going to talk about that. And that it's often referred to as an unlinked vulnerability or an unlinked exploit. And so I'm going to do this through, so the example that we're going to go through in detail is using an open source application called Chocolate Doom. So for, well, I don't think the millennials played a lot of Doom, so maybe, yeah, some millennials played Doom, right? Yes. Okay. So Doom was a game released in the 90s. So this is the first version of it. It was very popular. It was probably the game that made like the first person shooter kind of thing be a thing. It had fantastic graphics, as you can see. It actually has like a fake 3D kind of world. It's not actually 3D. It's a really like interesting game. It was written in C, and it was open sourced in 2007 or something, I think. So the code, the Linux port of it was open source then. A lot of source ports of it has happened that have ported it to various different platforms and also to various different graphical frameworks, windowing frameworks, and things like that. One of the most popular ones is Chocolate Doom. And so I got COVID. Not now, but I did, in January. And then I got really tired, and I was like sitting in bed, and I couldn't do anything, but I was also like really, really bored. And so what I did was I took a port that had been done by a guy in the C++ community called Jason Turner. He made a C++ port of this, because this is a C application. And so I spent, my entire COVID period just finishing that. So I had to use it for something, so you're going to get it here. But as a part of making this presentation, I wanted to go and see if this application also had this kind of vulnerability. And luckily for me, it did. So we're going to look at zmalloc. So this is a C API that's built into Doom. It has two different implementations, but basically the idea is that it's going to allocate memory for you. But it also has some kind of metadata that it stores. We'll have a little bit look at what that means, but not too much. We don't care too much about the metadata itself. We just care that it's a linked list. So if you're going to call it, so here we have a typical call. So we call sed malloc. We call it like we would do malloc normally. We cast the return value to the pointer that it's supposed to have. It's going to return like a void star or something. It's going to return a void star. And it has some kind of like extra parameters here that's like tag and user, but we don't care too much about that. So this first section here is the thing we're going to return from malloc, right? So this is this void star pointer. It's going to be the size of the thing that we're going to allocate. But in addition to that, zmalloc will also allocate space for this mem block. So this is the metadata section that comes before the section that has the data that we're going to give the user a pointer to. And this kind of structure is exactly the kind of structure that that Solar Designer went after in this kind of technique. So if you have a look at memblock T, so this is going to be in the implementation for zmalloc, which is called znative, for anyone who wants to follow along at home. I'm using my file path, but it works for Chocolate Doom, so then it will be znative.c. So this is the memory that we're going to allocate, and this is the memblock T that comes before that. And so here we have the structure. So it has like some ints, void star, and then this previous and next pointers. So this was the tag we saw on the previous slide, and this is the user that we saw on the previous slide, and we don't care about either of them really, but now you can see where they end up. They end up in this structure. What we're going to care about is this previous and next pointers here, and that's going to form a doubly linked list. So this is stored in the heap in this kind of manner. So these mem blocks are linked in this list that is linked to from a global. Everything is a global in this wonderful application. In this global global array called allocated blocks. And so we have a linked list that it links like this. A doubly linked list, for people who don't remember their computer science, is a list that has both a next and a previous pointer. But you'll see more of that. So the idea here is, and the most important thing to see here, is that, can I point with this one, do you think? Okay, I'm going to point. Is that the mem block is right next to the memory that was allocated. That's like the important thing to notice here. Is it a laser? Oh, a very small laser, but you can see here and here, yeah. Okay, so if we go here. So we're going to look at exploiting the free function, which is called zfree. I think the Z is for zone malloc, I think is for. So the first thing that free does is try to get a pointer to the memblock T. So it takes the pointer that was going to be freed, so PTR, and then it will subtract the size of the memblock T to get a pointer to the memblock T. If this is not your programming language, don't worry about it. It's not really important. The important thing here is that in the middle here, we're going to call a Z remove block. Okay, so this is Z remove block. And what we will see here is these two operations. So anyone who has implemented a doubly linked list at some point, which is probably a long time ago, then this is how you do the typical unlinking, right? You say, my previous is next should be my next. I'll show you. There is a picture. Anyway, let's do the picture. So here we have our block. So here we're going to do the line 8 first. So block next prev. So that will be the blocks nexts prev, which is this pointer over here. We're going to set that to blocks prev. So that is basically just bypassing our block, and then we're going to do the same thing with the other one. Ooh. And so that's how you do like a typical unlinking. And this will be useful if you get a really, really bad whiteboard interview, then it's like, okay, this is review for you. So there's a couple of insights to this, but the basic underlying insight here is that if you can control both sides of an allocation, so both sides of an equal sign in the application, then you can create what is called a write what where primitive. It means that if I can decide where we're going to store a value, and I can also decide what to store there, then I can basically write whatever I want wherever I want in memory. We'll look more into that. So if we look at the same code again, like condensed a little bit like we did before. So if it can control block prev, then we can control where the allocation happens, adjusted for the offset of next. We'll look at that later. But I'll just okay, so here we have the where. And if we can control block.next or arrow next, then we can control what to write there. So that's the other side of the equal sign. So that is the basic idea. And of course, you've already seen that block prev and block next are both next to each other in memory, right next to the memory that was allocated, right? And we also know that they are going to be used in this manner when we free, right? So the idea here is we're going to do a little bit of a memory corruption, and then when the block is freed, it will do this assignment for us. So this is often referred to as a write what where primitive. And you can, in this case, you can do it anywhere in the application memory. And if this was in, it was a privileged process, then you could do it in kernel memory. Okay, so the proof of concept here is very. I'll go through it, but basically the idea is that we're going to corrupt the pointers. And then we're going to free the memory, and then we're going to show that by freeing the memory, we can execute our write what where primitive. Okay, so up here, I have 3 allocations here. That's just to make sure we have a list. So I want to have a next and a previous. So it's the middle one we're going to go for. So we've allocated it here. Here I'm doing the same as before. Basically, I'm just trying to get the pointer to the memblock T. And here I'm going to prepare where I want the write to go. So that's this where pointer. And then what I want to write there, which is 42, 42, 42, 42 in hex, which is what the cool hackers do. And the fact that I said that means I am not one of them. And here I'm going to do the adjustment for the distance to next. I'll show you again later, but basically the idea is that when next is accessed, it will add the distance to next from the beginning of this memblock T. And so here I'm just subtracting the same distance, so that when the add comes later, it will be the actual pointer. If you didn't understand that, it's fine, but I will explain it again. So on previous, I'm going to write where, and on next, I'm going to write what. And then here's just an assert to see, okay, so right now, where is a null pointer? And then we're going to call free. And in free, we're going to do this unlinking will happen. And then afterwards, where is no longer null, and what where points to is this 42, 42, 42. So I found this, and I didn't really know what to do. Because it felt like very silly. I'm going to report a vulnerability on a game that was finished I don't know how long ago. But I did. I reported it. I submitted a PR, and they took it into the Chocolate Dooms. And I have a commit on Chocolate Doom. It's wow. But yes. So where has been set to what? But let's look at this a little bit more graphically for those who are inclined that way. So the previous pointer block, instead of pointing to what it should do, which is blocks previous, it points to, let's see, this thing. And here we have adjusted for next offset. So we basically subtracted the offset of next. And that's, no, I actually have it on the slide, Patricia, yes. So give me a second, I'll show you. And then we have where, and then on the next pointer we have what. And right down here, I'll try to show you. So the block arrow previous, arrow next, is actually block arrow previous plus the offset of next. Right, so that's what I do here. I just adjust for it by subtracting the same amount because it's going to be added later. Yeah, so there's a traditional mitigation for this, and you will find it in most allocators or many allocators today. And it's very simple. It's basically just checking that the pointers point to what you think before you do something. And this was basically my patch as well. Not exactly this, but I had to fit it on the slide. So here we are checking this pointer, right? So we're checking that block's previous is next is block. And if it isn't, we just exit. And then if it is, then we can do the moving of the pointer. And then the same thing here, we're going to check that blocks is next is previous is block. And if it isn't, then we exit. But if it is, then we're going to do the wonderful moving of the pointer. Yeah. So this is it's like this same check has been implemented like a ton of different places for this exact same thing in many, yeah. So how would you exploit this in real life? Because what I showed you was a C program, and you're like, Patricia, yeah, of course you can do like, you can do something, or you can use malloc and then do memory corruption and then do free, and it's not like super interesting. And usually what you would do instead, you would have like some kind of heap buffer overflow. So if you had an object next to this object in the heap, then you would do a heap buffer overflow, and with that overflow, overwrite these pointers, and then when that object is freed by the application at some point in the future, then your write what where primitive would run. So how would that look like? So this is our object to be freed down here at the bottom. And then we're going to have the layout of this drop and block thing above here. So this is, let's see, okay, give me a second here. So this is for 64-bit platform. So the int, and a 64-bit platform where an int is a 32-bit, because of course this is not defined. The size of int is like, woohoo, surprise. But this is a normal platform. And then over here we have, on top of this, we're going to have like the object that we're going to do the overflow. So imagine that this is some kind of buffer that has a heap buffer overflow vulnerability to it somehow. And so when the overflow happens, the writes will go down here, it will overflow the fields of the struct, and then it will overwrite the previous pointer with the where and the next pointer with the what. And then later at some point when the object to be freed is freed, then this assignment will happen. Okay. So this technique was presented in 2000. You know, way back when, what was it? Taylor Swift was 11. So let's go to 2019. So in 2019, this same technique was used against Android in an exploit that it has been named Bad Binder, and it was discovered sort of through intelligence gathering and then trying to narrow down where the vulnerability was. If you're like super interested in this, there's a really great talk at OffensiveCon last year by, oh gosh, Maddie. Okay, I'll tweet the link to it later. Yeah, so this is the CVE number for it. For people who are not familiar with it, this is sort of like a global bug database for vulnerabilities. And so it has the 2019 is the year, and then there's like just a number increasing. Okay, so from the CVE, it says use after free in binder.c allows elevation of privilege from an application to the Linux kernel. But when it was discovered, they didn't have that much data on it. But before we get into that, I just want to give you some very, like the shortest intro to Android IPC you've ever had in your entire life. So if you've ever done like Android development and making apps and stuff, you know that there is this wonderful IPC mechanism, which looks basically like a function call or a method call. You can generate this the API that you program against, and then you can call. You can do calls into other apps or services or things running in other processes. So this is a really nice feature. And then, and like from other platforms, you might, yeah, I've done IPC before. So, but Android's IPC is kind of cool. Like its legacy comes from Palm. So they, okay, for the Zoomers in the house, we used to have something that kind of looked like a smartphone, except you couldn't call anybody. Yes, and it was, and they were called Palm Pilots, and rich people had them. Yes. But basically the idea that came from Palm and that was inherited into Android was this idea of having this kind of kernel driver. And so there's this kernel driver here, and when the call goes, it actually does a context shift into the kernel driver, which schedules the callee in to get the message. And then when the message is over, it does the reverse and all the way back. So this means you can get basically a synchronous function call from an application to another application. But it does involve this, this kernel magic. So this was for a long time patches on the kernel, Linux kernel. I think it still is. Or no? Did they merge it?
I think by merging now.
Okay, yes. And it is a super cool tech, in my opinion. And it's basically a lot of like the underlying cool stuff in Android that made Android cool, in my opinion. Anyway, so, but how this was received at Google was basically they said that there's NSO group apparently has a vulnerability in Android. And the question was, what is this vulnerability? All they got was that it was being used in the wild, and it was being used to do surveillance on people. And for people who don't know, NSO Group is an Israeli technology firm. They make something called Pegasus, which is basically spyware, and they sell it to everybody. Okay, no, that's not true. They sell it to governments and law enforcement agencies everywhere. Which basically means that it's basically used for all sorts of surveillance of journalists, activists, it's just in general like evil stuff. And that's my personal opinion, which is correct. But anyway, so what Google got was that it is being used by Pegasus. They are selling this capability that they can root an Android phone and do surveillance of it, but they didn't know a lot about it. So basically, what they gleaned was basically from sales pitches from the NSO group. They had a bunch of different things that were available. I'm just going to say a couple of things. So oh, give me a second, there. So they were told it was an arbitrary kernel read-write primitive, and this means that you could read whatever you want, or you can write whatever you want in the kernel, so in the memory. And also that this config debug list property breaks the primitive. So if this was on, it didn't work. There was a bunch of other things on which kernel versions and things like that, and again, I will tweet the link to the offensive con talk after. But I just wanted to show you this bit here. Because if you had config debug list on, it would enable this. And if you squint a little bit, you might recognize what's going on here. It's going to check that previous is next is not equal to entry, or next is previous is not equal to entry, then it will panic corruption. Yeah, so this is familiar because this is the standard unlink vulnerability mitigation. Now this was exploited in a different way. So here they were using a use after free, and the whole chain and how it's done is more is explained in the talk that I will tweet. But a typical way that something like this could be exploited with a heap use after free is like this. So if you imagine that this is our heap, and we have our previous and next pointers up in there, then this section of the heap is freed, like something like the application freed this memory, and the previous and next pointer are still there, but they're like junk now. And if you have any access after this, it might be okay. It will be a use after free, but you won't die. But in exploitation here, one way that you could do this is that you could have this memory allocated to you, and then you can fill it with something else. So in this case, you might want to fill the previous and next pointer with your what and your where. And then later on, when the application does the use after free, it will execute your read-write primitive or your write-what-where primitive. So that's how that could be exploited. Actually, how it was through a bunch of different Linux system calls. But since the unlinking itself is done in privileged code, this becomes a use after free, leading to an arbitrary kernel read-write primitive. And then this was used to overwrite some address limits in the kernel, and then suddenly you had access to write wherever you wanted. Yes. So how would you find this type of bug today? Well, the good thing is that we have address sanitizer today. So address sanitizer was introduced in Clang 10 years ago, more than 10 years ago, I guess. Was quickly adopted into GCC. Then there was, I think, one made for the Linux kernel, which was KSAN. And there's been one made for almost every kernel, I think. And more recently, also adapted for the MSVC compiler, so for the Microsoft compiler. And so it is basically everywhere now. So address sanitizer is a way of instrumenting loads and stores for memory to be able to detect access out to bounds in different ways. And this works on the stack, on the heap, in the global memory, like all over the place. So running with address sanitizer, you would have failed on this. And since so I have certain aspects of my personality that doesn't fit well with security culture. So one of those was that when I found a vulnerability, I made a unit test that was the exploit, and then I put it in CI because that's what you do. But then I had to turn off the exploit on the builds where I had address sanitizer, because then they would fail, and you don't want builds failing in your CI. So, but address sanitizer is great. It's available on basically every platform. So if you're doing any kind of native development, definitely look into that. So address sanitizer would have found this if you exercise the code in this manner. And that's where address sanitizer kind of, it won't do magic. It's not enough to turn on address sanitizer in your builds on your CI and then run, your tests. If your tests are not exercising the code in this way, it will still not find them. So the recommended way to find things like this is by using address sanitizer and fuzzing. I'm not going to talk about fuzzing here, and that is also the number one way of finding memory errors today by security researchers when it comes to this kind of exploitation. It's a combination of address sanitizer with some kind of fuzzing with a feedback mechanism. Okay, but let's go to 2002. I'm not going to go in increments of 2, okay? Actually, okay, I love this. Okay. For all of you who actually remember this, it was awesome. Okay, so it's awesome for many, many reasons, but okay, so this song came out in 2002, and she's writing on this fantastic Nokia phone with a full keyboard. It's awesome, but writing a text message in a spreadsheet, and it was great. We loved it. Technology was, this is peak technology. So 2002, 20 years ago, Nelly was superstar. With the hot in, I can't even say it, hot in her, and Dilemma with Kelly Rowland, which had this wonderful scene, by the way. Actually, I think I'm just going to make a thread and the theme songs for this for this presentation. Okay, so in 2002, there was a post in Frack Magazine. So Frack Magazine was an online magazine that has been in, I think, at least 30 years, maybe 35 years or something like that's been going. So it goes back all the way to when we had the phone phreakers and things in California. And it's basically just publishing lots of articles by hackers on lots of different things. And so this one from 2002 is basically just a tutorial on different types of integer overflows, which is what we're going to talk about now. So saying 2002 is just being generous. This by 2002, integer overflows were old news. But let's have a look at that. So if you are a C++ or C programmer, the distinction between signed integer overflow and unsigned integer wraparound are super important. But if you are not, you don't care and it doesn't matter. So one of them is undefined behavior, the other is not. For the sake of this presentation, it actually makes no difference. So the typical scenario that you want to attack with some kind of overflow wraparound is this type of scenario. So I'm going to show you a type of scenario, and then I'll show you how it can be exploited in different ways. So here we have an if. We're saying that first length plus second length is less than buff length. So let's have a look at what this looks like in picture form. So we have this first, which is some kind of buffer. It has some kind of length. Then we have second, which is some other kind of buffer, and it has another length. And then we have this buff, and it also has a length. So the idea that we're trying to do here is we're going to try to copy first and second into buff, and we just want to make sure that there's no overflow here. So we want to see, basically ask, does first and second both fit into buff? That is the thing we're trying to figure out. And so down here on line 1, you have if first length plus second length is less than buff length. Now, if you're from most other computing languages, you do have wraparound for your assigned integers, and you probably don't even have unsigned integers. But C# has unsigned integers, right? Yep. Yeah. But they're going to wrap around anyway. So it's fine. The problem here becomes, what if the attacker can control what you are thinking is the length of one of these? So I'll show you on the next slide. Okay, so here we have the same code we had before, but here we're going to be lying. So we have an attacker-controlled length of second, and here, imagine an attacker-controlled buffer as well. And then the rest of it is the same. So the problem here is that when we send max int as second length, when we add any kind of smaller number to max int, it's going to wrap around, it's going to become a small number. And this small number is going to be less than buff length, and so we're going to pass this if test, and we're going to do the copy. And that's going to give us a buffer overflow, right? So if this is on the heap, then this will now give us a heap buffer overflow. It's on the stack, it will give us a stack buffer overflow. Yeah. A different way is, so then you're thinking, okay, but I'm going to allocate buff to be the right size. So instead of like having a buff length, we're going to calculate it. So we're going to do, instead we're going to say buff length is equal to first length plus second length. And then we're going to allocate that size. And then we're going to do the copy, you know? But unfortunately, you know, lying works. So now we're going to do with an unsigned integer overflow. Unsigned integer wraparound. Ugh, slide is wrong. So because the same idea happens here, right? There's going to be an overflow. It's going to overflow around, and the result is going to be a small number. For signed integers, it's probably going to be negative. For unsigned integers, it's going to be a small but positive number. So here we are allocating a very small buffer, and then thinking it's fine, and then we're going to do the copy, which is going to cause our overflow. Okay, so this is the basic idea of that technique. So we had this article in Frack Magazine from like 2002, where this was considered in the security community to be known knowledge. Like this was like everybody knew this. Okay, so let's go to 2017 and to Chrome. So I'm going to show you just. So this is CVE 2017-15-416. And if we go and look at the CVE, it says heap buffer overflow in Blob API in Google Chrome allowed a remote attacker to potentially exploit heap corruption. So I'm just going to show you the fix, because I think it's enough to show you kind of how this works. So this is the patch. So this was the vulnerable code. So here we have some addition of typical like an offset and a length, and then we're trying to see if that is greater than total size. And instead it was replaced by this code underneath here, where they are going to check if adding these two will overflow or not. If it doesn't overflow, then it will assign it to this local variable called nbyte, and then that is used for the comparison. Yeah. Okay, so let's go to 2021. And here we have a vulnerability in Apple iOS and iPad OS and Mac OS and all of the Apple-y things. So it was 2021-3860. So from the CVE, an integer overflow was addressed. Processing a maliciously crafted PDF may lead to arbitrary code execution. So this is the code that has the vulnerability. We won't go in detail. I'm just going to like highlight the interesting sections. So here we have a 32-bit unsigned integer, and here we are incrementing that integer with attacker control data. So now we can put in like a huge number here. Then we are using that number that has been incremented with attacker controlled data to allocate the buffer. So if we manage to make it wrap around, then at this point we're going to allocate a buffer that is too small. And then when we actually do the copying into the buffer, we are going to have our overflow. Yeah. So how do we find those? So for signed integer overflow is as I mentioned, is undefined behavior in C and C++. That doesn't mean anything outside of our communities. But it basically, for tooling purposes, it means that the UB sanitizer, undefined behavior sanitizer, will find them. So if you manage to provoke this kind of behavior in the code, then it will then UB sanitizer will scream at you. For unsigned integers, it won't, because it's not undefined behavior. But there's an integer sanitizer that will tell you. Almost always, any kind of wraparound or overflow of an integer, either signed or unsigned, is usually unintended by the programmer. It's because it's not normal for like a human being to think that if you increment a number, it's going to become smaller. It's just, human beings don't work that way. There are some features in C++20 that will help with some of these things, and there might be more features in the future to help making these kinds of comparisons and incrementations safer. But let's go to 2010. And actually 2010 here, I'm just being extremely generous. So this is 12 years ago, where Rihanna had the absolute fantastic song Rude Boy, and Lady Gaga had Bad Romance, because Poker Face was like a couple of years ago already. Can you imagine? Wow. 12 years ago. Also, of course, this man, who some of you might know, released this product, which was like a really oversized phone, and not like too small to be a computer, too big to be a phone, and what would we ever use it for? So the iPad came out in 2010, the original one, which was like really thick. But also, in Frack Magazine, in 2010, came this wonderful post, a eulogy for format string vulnerabilities. So this is when the security community felt, it's over. There's no more fun to be had with format string vulnerabilities anymore. They had the post in 2002 going like, advances in format string exploitation, but by 2010 they were like, it's over, people. And there were good reasons for this. Like a lot of applications had fixed a lot of these, but also compilers had implemented warnings around these. So there was a lot of people had fixed a lot of this. But, everything that's old is new again. So to understand format string vulnerabilities, I'm going to give you a very quick introduction to weird format string features. A couple of lesser-known format string features. So even if you don't know a lot of C, you've probably done a printf at some point in your career, and that's all you need to know for this. So printf has like a ton of fun features. One of the features that you probably know is, of course, that you will pass in a string as a first argument, and then you can pass in like all sorts of like as many more arguments as you want, hopefully matching the where they should be replaced in the format string. But this is C, and we play fast and loose with things. But in this case, we're going to do like a really cool feature. If you're going to make like a terminal application in C, this will be very useful for you. So the idea here is that if you want to make like columns maybe, and you want things to align properly and things, you can use this property here. So here we're saying that we want the column width to be 17 characters. And then we're going to print a D, which is an integer. So we're going to pick that from our arguments, which is then 10 right here. So that means that we're going to use 17 characters, but printing 10 as a part of those 17. And you can also do this, where you can actually pick the field width also from the arguments to printf, with this wonderful star functionality. And I'm not going to go into this, but this is direct access, and this means you can like pick and choose which one of your parameters you're going to use for this. So this is one feature, but this feature is probably the most important. So this is let's go have this small program here. So here we have this integer num. And then we're going to do a printf A, B, C, D, E, F, and then percent %n, and then the address of num. So we're passing as our only argument a pointer to num, which is here, and then we're going to print num. So if we do this, we run this program, it will print A, B, C, D, E, F, and then it will print 6. Because this feature is that the printf will actually write to memory how many characters it has written. Now, printf vulnerabilities has been used for a lot of fun stuff. Today, often the ones that are found are used to leak memory. So because you can, if you can control the format string, so the first argument to printf, and the best way to do that is if you have any code that takes a user input of some kind, and then it just does printf variable, end brace, semicolon. then that attacker-controlled string is actually a format string, and you can put whatever you want in there, and it will just grab stuff from the stack, and just it's just going to go like, I assume the stuff is here, or in registers, or depending on the platform how this is implemented. So it's a good way of leaking memory. But with %n, it also writes memory. So it doesn't only read memory. With %n, it can write memory as well. And you can combine these two in fun ways. So here we're using field width. With 42 is our field width. And we're also using %n. So when we run this, it will print a 1 way over there. And then it will print 42, because we said that the field width should be 42. And so in this way, you can also dictate what values are written to memory, because that is also a part of the format string. And this is just a very brief introduction to like weird stuff you can do with format strings. And from personal experience, it's a terrible way to write an exploit. It's really horrible, and I do not recommend. But because you're basically programming using like %s, %d, it's really, really bad. But, it works. Okay, so we were, a reminder, we were in 2002. That's when we had advances in format strings. By 2010, it was like, it's over, people. I'm sorry. A eulogy for format string. But 2021. So, Apple, iOS. So some of you might have seen this on Twitter, because it was actually released on Twitter. So this is CVE 2021 3800. And from the CVE, it says, joining a malicious Wi-Fi network may result in a denial of service or arbitrary code execution. So I think the tweet will not be like super surprising. If you notice here, it says, after joining my personal Wi-Fi with the SSID %p, %s, 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 %n, my iPhone permanently disabled its Wi-Fi functionality. Neither rebooting nor changing the SSID fixes it. Because the whole Wi-Fi stack, if I understand correctly, just wasn't a cyclic reboot, because it kept on like discovering this thing, and they probably had some code that went printf SSID somewhere, and so it will just crash and crash and crash. Yeah. Okay, so how to find them, right? So of course, with any kind of %n, you're writing to memory again, so you're probably going to find them with address sanitizer. But also, GCC and Clang have had format string warnings for many, many years. And this is also a shout out to the technique of compiling your program with many compilers, which is a very good thing for finding different kinds of bugs. Okay, so we have this split here between systems programming and binary exploitation. And unfortunately, for me, the overlap between these two groups is very, very small. And if you talk to a lot of people who do binary exploitation, they will just tell you that they're really terrible programmers and just write shitty C, and that's all they do. On the other side, you have C and C++ programmers who generally don't really know how this exploit business works. And so we need some kind of overlap here to learn from each other, or we're going to continue making the same mistakes over and over again. So we had this span in time from 2000 to 2022. And we keep on seeing bugs that we should have been able to eliminate a long time ago, but we keep on making the same mistakes. And so, yeah, so we'd like to think that we're living in the future. We have the technology. And the MP3 players are much better now than they were in 2002. I have to say, I think it was like 2001 when the original iPod was released, which I still think is like an awesome piece of technology. You could it had a hard drive. You could have all of your music in there. It was awesome. For its time, it was absolutely amazing. And okay, sorry. I got distracted. So we like to think we're living in the future, but maybe we're just kind of living in a more like functional version of 2000. So we need some way to have the past inform the future, and that requires us to learn from each other and be open to listening to people from other communities, and maybe have more of a cross-pollination between communities, where we actually go and talk and listen to each other more. And the funny thing is, I'm going to do a version of this talk at a C++ conference on Friday, and they're going to understand parts of this presentation that maybe for most of you was like, woohoo! But they're not going, like some parts of this presentation that you probably thought was like totally normal, they won't understand. And so this whole talk is kind of balancing that edge between these two communities, trying to like kind of show the two sides of the same coin. And I am a C++ programmer, so I also have to say that, you know, don't hate on C++ just because of this. It is a really fun language, and it's an amazingly complex language, but it is super fun. And I just want to thank you all for coming. And if you have any questions, I do have a few minutes. Yes, okay, clap. Any questions? Come on, one question. No, nobody wants. Yes.
Okay. Well, I don't know a lot about this, but I didn't understand the integer overflow vulnerability. The consequences of it, if you override the buffer, will it just lead to a crash, or can you exploit it to write a new one somewhere?
Yeah, for example, we could use it for the first one, right? Because for the first one to do the exploitation of the, let's see if I can go back to the slide. I'm really good at Macs, by the way. Okay, that was, let's see if I can find that. So if we go to here, let's see. So imagine that the overflow that we had was here. Right? So we had a buffer that was allocated on the heap, and we had an overflow vulnerability here. So now we can overwrite down here, overwriting here with the where and the what that we want. Later on, when this is freed, then we will we'll do our write what where. And that's often what you see today, is that most exploitation of modern applications involve a chain like that. So you will have, for example, a heap buffer overflow leading to this use after free, which, you know, things like that. So yeah, it's a good question. Yeah?
This exploit actually, the one you showed, they're available, I mean, can they be exploiting C# as well? Or is it just
Well, okay, so my experience with C# is like very small, but I have like a talk. The thing is, what you will often see with vulnerabilities in C# and Java and things, if you're going to go for native vulnerabilities there, you'll have to go against the virtual machine in some sort, or against some kind of native API. Anytime C# is using some kind of underlying native API, but you will also see, for example, in another type of managed language, which is like JavaScript, and then it's often today going against the JIT, and creating memory errors in the JIT, the just-in-time compiler. And you could probably do that with C# stuff as well, but it's not as interesting, so I don't think the research is like as advanced, because it's much more fun if you go to a website and that causes you to be exploited locally. Yeah. But I'm not like a super expert in C#, sorry. Yeah? Well, the plan is, okay, so the plan is, so my plan is that I want to make a follow-up training to my Insecure C++, and the idea there is that the whole training is going to be exploiting Doom, basically. So I'm basically now just like looking around, finding vulnerabilities, and then the idea is that the students will then set up chains and then do stuff like, I don't know, like get more lives or shoot or I don't know stuff. So that's the plan. I haven't gotten that far with it yet, but it's the beginning of that. Yeah. Any more questions? Oh, yes, go.
Yes, I was wondering, is it possible to exploit this kind of exploit if you're running in the cloud? Do you need access to the host to do it, or am I safer in the cloud? Nobody accesses it.
Okay, are you safer in the cloud? Well, the thing is, this type of application basically is based around getting, and that's the same true basically for anything. You need to get your data in somehow, and if you're running in the cloud, you are getting data in somehow, or you're just standing there and not doing anything. So you're getting requests, you're getting things. Anything that you're running on, any vulnerabilities there will be an issue for you too. So if any kind of like, for example, you had, many years ago, you had Heartbleed vulnerability, which would then, leak all of your keys in the cloud. And anything that you have that is accessible from this virtual, this container or whatever it is that is running, will also be accessible for anyone who has breached you. And so that would be all your customer data and those kinds of things. Yeah, it's, and I think today that's probably more popular, like going after cloud stuff, because that's where the data is. Yeah.
I was basically going to add to that. My original question was, what exploit is there really for Doom? Because you're running Doom as a local user, it doesn't have special privileges, it doesn't do much network communication, if any at all. So by exploiting Doom, what do you actually achieve? And then the flip side of that is that when you run stuff in the cloud, it's all based on network transactions and running on other people's systems. So I would say that an exploit is much more likely in a cloud scenario, or it's much more damaging in a cloud scenario, certainly, than it is for a local application like Doom.
Yeah, no, okay, so let's, let's see if I can, because I forgot to repeat questions earlier. So how would you, if you want to go, you can go, by the way, okay? I won't be offended. What kind of interesting ways can you attack Doom? So one of the cool features of Doom for people who were like playing with Doom like in the 90s was also that it had like network playing. So you could play on your local area network with other people also playing Doom. So you had multiplayer capabilities, but like in the LAN kind of scenario. Okay, this is like for, I'm sorry, young people, but it was the technology at the time. So there was a network player mode for Doom, but also in addition, you had to load the game from a file, and you also have saved file. And saved file or save game files have been used to root lots of different devices. And also the game itself, it's a binary file, so you have to download it from the internet. And so it's a typical like pirating kind of thing. You're just going to go and grab a file from the internet and you run it on your machine. So there are hopefully a bunch of different ways that we can, and if there's not enough ways to make it vulnerable, I can make new ways. That's the whole point. Yeah. Any more questions? Yeah?
Wouldn't the ultimate solution for these kind of vulnerabilities be to move to languages that enforce?
Rude. Okay. So the truth of the matter is that basically, even if you're in a managed language, what you're running on is usually written in these languages. So your operating systems, your compilers, your VMs, so it's fun for me to go to Java conferences because I can go to any kind of Java talk that is like from the people who are making the VMs. It's just C++ all the way. It's like when your VM crashes and it says segmentation fault. It's like, yes, thank you. This is our world. So yes, you can live in sort of like a pretend environment where you can abstract yourself from the machine, but the machine is always there, and it is always, it's just, it's bits all the way. But yeah, I love that. I think this is fun. So Any more questions? No. Okay, go.